Good afternoon, everyone. I appreciate you attending this virtual presentation. I'm going to talk today about using predicted collisional cross-section and other analytical values and model metabolomes as a way to describe the current and future potential of ion mobility mass spec in non-targeted metabolomics experiments. Now, really, this is a talk today about resolving power and resolution. I think everybody knows that the metabolome is a physiochemically complex sample type, but we're also confronted with the issue that the metabolome components are also too similar to each other in many cases, that is, isomers. So to deal with it, we need many forms of resolving power. These forms include sample preparation. The one we think about most frequently is mass resolution. MS-MS fragmentation is a resolving dimension. Chromatography, and finally ion mobility spectrometry, probably the newest addition to our toolbox. Now, resolving power can be calculated simply as the mass, in the case of mass resolving power, the mass divided by the full width half max. So a typical resolving power in the mass dimension is around 40,000 for a time of flight instrument. Full width half max is the simple product of the standard deviation times 2.355. So this is a relatively simple Gaussian calculation that we can perform. We can calculate resolving powers as well for CCS and retention time. CCS typical values are around 40 and retention time around 500. Now, ion mobility, just as a brief overview to make sure we're all on the same page, is the separation of ions in the gas phase by shape properties. From ion mobility, we can frequently derive a collisional cross-sectional area of an ion as it moves through the gas phase. And what this offers is the potential separation of isomers. Now, this is a fast separation on the milliseconds to seconds time frame. Now, there's many forms of ion mobility. These include traveling wave, trapped ion, drift time, and field asymmetric ion mobility spectrometry. The CCS values I'm going to talk about today are traveling wave predictions. But the theory that I think I'm presenting here is probably universal to all of them. Now, one of the limitations of mobility to this point has been in relatively moderate resolving power, 30 to up to 200 on commercial instruments. But there are instruments in the developmental stages and in research laboratories that can get much higher resolution, including the SLIM devices and the IMS devices, with SLIM, I think, holding the record over 1,000. So the question is, does IMS add value to non-targeted metabolomics experiments? And I think that the short answer is that yes, we know that it can, because CCS has been demonstrated to resolve some isomer pairs, and it can reduce the list of possible IDs. I think this is what our literature has told us to this point. But what I'm trying to attain here is a bigger picture, more probabilistic view of what IMS can add. That is, for any given metabolome, how likely is IMS to improve our data? What do we gain in utilizing it? And finally, how much value can we expect IMS to add? That is, we want to enumerate some of our chances of success here. But there's a problem in trying to tackle this goal. The first problem is that we have a finite number of measured CCS values. This is a relatively new technology, but there's also the limitation that standards are often not available for many of our metabolome components. So we can't always measure CCS. And second, just as critically, is that we have limited knowledge of any given metabolome composition. That is, if you hand me a sample, I can't tell you all of the metabolites that are in it. So the approach we're going to take here to try to derive this big picture view is to use model data to derive resolution probability estimates. To do so, we will use the HMDB family of metabolomes. These are some of the best curated metabolome data available, and we have several of them to choose from. So these will be model metabolomes, so to speak. Then we will use predictive properties. So we will take all of the compounds from these libraries and predict CCS, retention time, and mass to charge ions, so our features. Now, I want to make a point here. These predictions are inaccurate. They are imperfect. But I also want to point out that they do not need to be perfectly accurate to derive a probabilistic big picture view. We have some assumptions that I'll go through later, but the prediction accuracy isn't critical. The methods that we'll use here are to download the HMDB serum, urine, and feces databases, as well as FoodDB, a larger natural products type database. All of the calculations are done in our environment using the packages listed here. we're going to make some assumptions that our mass resolving power is 40,000, CCS is 40, and retention time of 500. From the databases, we're going to extract SMILES, descriptions of the structure, filter the redundant, and predict CCS using a machine learning method that you can find described in TP281. We will also calculate isotopic envelope for all adducts using the NVPAT package. Xlog P units coming from the RCDK package will be converted to retention time on the linear 40-minute gradient. You can picture this as a reverse phase Endohillic gradient to cover the metabolome. Now, we will consider metabolites as being resolved if their overlap factor, or metabolite signals as being resolved if their overlap factor is less than 0.1. If we have multiple dimensions in consideration, so for example, mass and collisional cross-sectional or IMS resolving power, the total overlap factor is the product of the individual. So what is the overlap factor? This is an example of what that looks like. You can see the overlap factors numerically described at the top of this plot. But if we have two Gaussian peaks, there is an area under which both of these peaks have space. And if we take the area of the overlap divided by the area of the peak, we have the area of the overlap factor value. So this is going to be a value between 0 and 1, where 1 is completely unresolved and 0 is perfectly resolved. So these are highly overlapping and we have a high overlap value. The overlap factor for two better resolved peaks is going to be very low. So you can see a tiny shaded area in the center of the overlap plot here. And in this case, this is an overlap value of about 0.02. So these would be considered resolved using our less than 0.1 metric. I want to point out here too that the overlap factor is asymmetrical. So if we have different features with different heights, for example, an M2 isotope versus an M0, the overlap factor is going to be different. The overlap itself is a fixed constant value, but as a proportion of the total area, they differ. So in this example, peak 1 is resolved from peak 2, but peak 2 is not resolved from peak 1. So some of the assumptions that we're making in this study, we're assuming that our prediction error is random and their variance is realistic. We're assigning the assumption that all compounds in these data sets are going to ionize as positive ions, as all three of protonated, sodiated, and potassiated adducts, all of which have an ionization efficiency of 1. That is, all of the ions have the same signal intensity, which will be distributed through their isotope envelope later in the experiment. And then we're also assuming that each compound signal is Gaussian and monomodal. And for IMS in particular, the monomodal assumption is probably not perfectly valid. And we don't know the frequency of this at this point, but bimodal distributions aren't rare. So let's look at some of our model data first to get an overview of our distributions. We can see, as expected, in the upper left that CCS and mass to charge are correlated, particularly in the case for Z equals 1, which is typical for metabolites. This is very expected and has been shown experimentally as well. Retention time and mass to charge in the upper right are more poorly correlated. You can see a small area where you do see stronger correlation, but in this case, the correlation is relatively poor on the metabolome scale. Likewise for retention time and CCS. It's worth keeping in mind that the metabolome composition dictates these relationships to some extent. And if we now look at the fecal metabolome rather than the urine, we can see that retention time and mass to charge correlate much more strongly. Likewise, retention time and CCS. So we're doing hydrophobicity-based estimates here for our retention time. And as lipids are polymers of relatively nonpolar units, we see a stronger relationship between hydrophobicity and molecular weight. So let's now start to look at our data. Let's look at isomer resolution, one of the areas where IMS is really offering something that others might not, other resolving dimensions might not. So we'll assume a resolving power of 40 again. And the process we're going through here is to determine all the unique molecular formulas for the monoisotopic protonated adducts. We then calculate all the pairs of overlap factors for each ion formula, and then finally determine the median overlap value for each of these formulas and plot. And this is what these plots look like. On the x-axis, we have the number of pairs of isomers for that formula at the log 10 scale for visualization. On the y-axis, we have the median overlap, with 0 on the bottom being completely resolved and 1 on the top being completely unresolved. And then we have on our z-axis a count value. So how frequently does a formula fall into that particular bin? And what you can see here is that we have a strong blue signal in the upper left portion of this plot, and we have relatively few values on the bottom of this plot. This is giving us an indication that there are examples that we can resolve isomers in this urine metabolome, but the majority of them are unresolved. And we see most of our signal toward the top of the plot, which is indicating that most of the time, in a probabilistic sense, our chance of resolving any given isomer pair in the urine metabolome is relatively low. And if we expand this and we look at all of our metabolomes, we can see that this trend holds in large part through all of them. That is, most of our signals are found above 0.1 on the y-axis. But you can also see that there are some database dependent patterns here. FoodDB looks appreciably different than the other human metabolome database submetabolomes, where in particular you can note that at the higher n pairs value, that there are many more points that are lower on the plot than we had seen with the other mammalian system databases. So now let's move to a second class. So rather than looking at isomers alone, let's exclude isomers and look at all of the mass features that can be found within 10 ppm of each other. And 10 ppm, just to give you an example of what that looks like, in this case, this example has an overlap of about 0.64. So if we look at all of these partially resolved features by mass, the question is how frequently can IMS improve that resolution? So if we look at all of those MZ unresolved features and we plot this as a histogram of all of the overlap values, we can see that we have sort of a bimodal distribution here where we have many features that are completely unresolved and many features that are pretty well resolved. And this is with mass spec only. If we add CCS to this, we can see that the number of unresolved features on the right with overlap values of 1 drops dramatically. And we can see that the bar on the left goes up proportionally as well. So what this is telling us is that CCS is actually effectively improving our mass resolution, or the probability of effectively separating two features with similar mass values. We could do the same for retention time, and retention time actually improves things further beyond what CCS offered alone. And this addition of retention time to our mass is one of the reasons everybody is using chromatography. You know, it's a very good, it's a very effective resolving dimension. And I think that is why we're seeing such a strong trend here is we have about 10-fold the resolution in chromatography than we do in ion mobility. But by adding CCS to it, we do see an increase in the number of resolved features further. That is, the number of completely unresolved goes down, and we move some of those toward the resolved section. So let's get a little simpler overview on all of this. If we look at the bar plot here, we have resolution type on our x-axis and the proportion resolved on our y-axis. We can see that with MS alone, we're looking at a value of about 0.48, so 48% of our feature pairs are resolved. We can improve this by about 20% by adding CCS. And we can improve it further by adding retention time. We get up to about 93%. And if we use all three dimensions, we get up to about 94%. So this is telling us that we are seeing a bump, that CCS is providing additional resolution to mass spec alone in the absence of chromatography by about 20%. And if we add CCS to chromatography and mass spectrometry, we see a relatively small increase in the number of features that are resolved. Again, we can expand this to look at the other databases. I apologize, FoodDB is still calculating, work in progress. But for urine is what we were looking at in the past. The previous slide, we can see comparable trends in the fecal and serum metabolomes, with a big difference being that we don't see the same maximal resolution in the fecal metabolome as we do in urine, or in the serum metabolome as we do in urine. And I think this has to do with the fact that retention time is less orthogonal to mass dimension in the fecal metabolome than in the urine, as I showed in the previous slides. So now I mentioned in my title, thinking about the future of ion mobility. And the fact is that current instrumentation gets around 40, but some of our commercially available and developmental instruments can get much higher resolution. So what do these plots look like if we assume a resolution of 600 instead of 40, something more akin to chromatography? And what we can see here is that all of that blue signal in the upper left tends to move toward the bottom of the plot. And even at some of the higher n pairs value on the x-axis toward the right, we can see many more signals down in the under less than 0.1 overlap factor region at the bottom of the plot. So once we can more routinely achieve resolutions like this, and instrument development will continue, resolution will improve, we can anticipate that our probability of success of any given isomer pair resolving challenge is more likely to be good. That is, we can resolve any given isomer pair. Look at this in a more quantitative fashion. We look at all the resolution values between 40 and 1,000 in increments of 40. We can sort of derive an estimate of where we want to be. So if we're looking at our median curve, this curve can be interpreted as a 50% chance of resolving any given isomer pair. And if you draw a line across at 0.1 and see where does it cross for each metabolome. And you can see that this is going to differ for each metabolome. With the urine metabolome, this is at approximately 270, for example. In the fecal metabolome, this value is not reached until closer to about 750. So the complexity and the structure of the metabolome is going to determine how much IMS resolution we need to achieve that 50% chance of success. So in conclusion, the lower resolution IMS that is routinely available now does improve metabolite resolution in the absence of chromatography by about 20%. Now this seems, to me at least, at first blush, like a relatively small incremental increase, but it's worth keeping in mind that this is a comparable effect size, for example, to adding negative mode mass spectrometry, negative mode ionization, to a positive mode experiment, or adding APCI to an ESI experiment. And of course, ion mobility is done within the normal experimental time frame. So this is appreciable and fast. Second is that our low resolution IMS with chromatography will improve metabolite resolution, but minimally. That is, since our high resolution mass spec and since we have good chromatography, there's only relatively little space for IMS to improve things. Now, with that said, if we have higher resolution IMS, it offers the potential for faster metabolome resolution. And we can start thinking about how better to balance our chromatographic resolution to enable faster or potentially no chromatography for improved throughput. I want to acknowledge a few funding sources, including the Waters Center of Innovation program. The NIH supports me in an informatics program, and the CSU OVPR for their continued base support. I want to thank all of the CSU proteomics and metabolomics facility staff for all of their productive discussions and support. And I also wish to acknowledge, especially in these times, our scientific societies, ASMS, of course, notably in this setting, but all of them for the support that they provide our community, especially during times such as this. Thank you all.